Hey Calc kids, welcome to 5.5 Substitution. Just giving you a heads up, this is one of my most favorite sections in Calc 1. I think this process is so super cool. We have learned pretty much everything you need to know about taking a derivative. Any function that's put in front of you, you should be able to now take the derivative of, or eventually with practice. Unfortunately, it does not work in reverse. Given a function and looking for its antiderivative is not so straightforward. 5.1 to 5.4, even the end of chapter 4, we talked about taking antiderivatives. We've introduced the integral notation. But we're going to come across a lot of roadblocks with taking integration. So we're going to start breaking down some of those roadblocks, and then in Calc 2, you will do tons and tons of different techniques for integration. So that being said, let's start talking about substitution. What does this mean? Let's suppose I gave you the function f of x equals the sine of x squared. Then the derivative of the function would be, well, don't forget the chain rule. When we have a function inside of another function, we take the derivative of the outside function. So the derivative of the sine is the cosine. We leave what's inside alone. Then we multiply by the derivative of what's inside. So the derivative of x to the 6th is 6x to the 5th. So I'm going to just rewrite this as, just so we don't mistakenly multiply these two together, because that one's inside the cosine, this one is not. So the derivative of the sine of x to the 6th is 6x to the 5th cosine of x to the 6th. So that being said, if we take the antiderivative of 6x squared, 6x to the 5th, don't change the problem, cosine of x to the 6th, the answer would just be the sine of x to the 6th. The derivative of the sine of x to the 6th is 6x to the 5th cosine x to the 6th. Then the antiderivative of 6x to the 5th cosine x to the 6th is just what we started with. Although we do have to pop on this plus c, because technically the derivative of the sine of x to the 6th plus any constant would still give us the cosine of x to the 6th times 6x to the 5th, because the derivative of the constant would just be 0 and it would go away, okay? All right, so let's try another one. So we're just practicing the chain rule right here. So let's suppose I gave you the function h of x equals the square root of e to the x plus 4. All right, then I'm going to rewrite this as e to the x plus 4. I turn all radicals into powers, right? So then the derivative of h would be, we bring the power out front, leave what's inside alone, drop the power by 1, and then multiply by the derivative of what's inside. And the derivative of e to the x plus 4 is just e to the x. So I'm going to rewrite this. Isn't this just e to the x? And then negative 1/2 power just means the square root of that in the denominator. And then the 2, don't lose the 2. Right? So if h of x equals the square root of e to the x plus 4, the derivative of h is e to the x over 2 times the square root of e to the x plus 4. So if I take the antiderivative of e to the x to square root of e to the x plus 4 dx, we should just get what we started with, the square root of e to the x plus 4. Because I started with e to the x plus 4, took its derivative, and then the antiderivative of the derivative, it's just the function itself. But we're going to tag on the plus c. So even though we didn't start with this, we actually did. We started with plus 0 up there, but I could add any constant up there. All right, so this would be it. So I'm not sure if you're seeing a pattern here. What the substitution rule is doing is reversing the chain rule. If you notice, what we did here was we did the chain rule, so we got a function. We had a function inside of another function. And then when we take the derivative of a function inside of another function, we see that function still inside something, then we see its derivative outside. So here we had x to the 6th inside the sine function. Its derivative has x to the 6th now inside the cosine function, but notice the derivative of what's inside appears outside. Keeping that in mind, what if I just said to you, tell me, what is the antiderivative of 3x squared plus cosine x times e to the x cubed plus the sine of x? What do you think? Well, the answer would just be e to the x cubed plus the sine of x, right? And I'll tag on that arbitrary plus c, because the derivative of e to the anything is itself, it's e to the anything, times the derivative of that anything. Notice there's the derivative of the power. 3x squared plus cosine x is the derivative of x cubed plus sine x. So what we do is we call this function the inside function, because it's inside of another function. And then this is the derivative of the inside function. It appears outside of the function in the integrand. Derivative of the inside function. So let's go back here. Right? So we're just looking at this integral right here. Here's my inside function. It's inside the cosine. Inside function. And 6x to the 5th is the derivative of that inside function. Right? When we look at this integral down here, don't look at what we started with, because we're not going to start with this. We're going to just start with this guy right here. And we're going to see this right here. Notice e to the x plus 4 is inside of a square root. So this is the inside function. And if you take the derivative of e to the x plus 4, you just get e to the x. So the derivative of the inside function appears outside of the square root. So that's what we're looking for. If we can see this pattern, then we can do a process called substitution. So I'm going to do integration by substitution by example. So here, this is the process. So let's suppose we started with 3x squared plus the cosine of x, e to the x cubed plus sine x dx. Right, now we ask ourselves, what function is inside of another function and whose derivative appears outside of the function? So here we can see that x cubed plus the sine of x is inside the power of e, and its derivative is out here. So this is my inside function. So this is my inside function, and its derivative is not inside the function, it's outside as a product, as a factor. Derivative of the inside function. All right, so what are we going to do? I'm going to do, hold on, I want a good color. What we do is let u equal the inside function. All right, so this is, my inside function is what we let u equal. And then we find du dx, the derivative of u with respect to x. And the derivative of u with respect to x is 3x squared, plus the derivative of the sine is the cosine of x. Right, now we're just going to do a little bit of algebraic manipulation here. We're going to take this differential and we're going to bring it over to this side. Because this is the change in u over the change in x, we're going to bring this change in x over to this side. So du really just equals 3x squared plus the cosine of x with respect to x, the change in x. That's just a little bit of a manipulation with our differentials. Not a big deal, but it will be super helpful. Okay, so these are the two things that I'm going to focus on right now. U is equal to x cubed plus the sine of x, and du is 3x squared plus cosine x dx. Right, so let's go back to our original function. I'll rewrite it up here. So my original integral was 3x squared plus the cosine of x, e to the x cubed plus the sine of x. Right, I'm just going to rearrange this, and typically in practice we don't do this after we kind of get the hang of it. X cubed plus the sine of x, right? I'm just rearranging these two factors, times 3x squared plus the cosine of x dx. Now I'm going to make my substitutions. 3x squared cosine of x, right here, I'm just going to replace this with du. And x cubed plus sine of x, I'm going to just call u. So now I'm integrating a whole new integral. I'm integrating e, and instead of e to the x cubed sine x plus sine x, I'm just integrating e to u, and I replace this whole quantity, 3x squared plus cosine x dx, with du. So integrating 3x squared plus cosine x e to the x cubed plus sine x dx is equivalent to integrating, with respect to x, is equivalent to integrating e to the u with respect to u. Now we simply integrate that. The antiderivative of e to the u is e to the u plus c. Okay, so now we're so close because we have to go back to our final problem. Our final answer has to be in terms of their variable we started with. So we started our problem with x's. So we're going to end with x's. Our final answer is the integral of 3x squared plus the cosine of x, e to the x cubed plus the sine of x, d of x is equal to this, although we're going to put back in what u equals, and u equals x cubed plus sine of x. So it's e to the u, but u we called x cubed plus the sine of x, and then plus c outside. And you can take the derivative of e to the x cubed plus sine x. You see that you get e to the x cubed plus sine x times the derivative of the power, which is right there. So that's it. So remember, what's super cool about taking antiderivatives is that you can check your answer by taking the derivative. All right. I'm going to write down the substitution rule. I think sometimes in math, when we look at templates, they're a lot harder than the actual process, but we will write it down. The substitution rule says that if you are integrating a function inside of a function, and the derivative of that function also appears in the integrand, that's equivalent to integrating f of u with respect to u, where u is equal to the inside function. So that's it mathematically. Let's try. Let's go back to this guy. This is one that we worked backwards. I gave you the answer. We took the derivative and then we integrated it. All right, so let's see what we have here. I'm going to do this in red. I see that we have a function inside of another function, and this one's stuck under the square root. It doesn't always work this way, but that's the first thing you should look for. Is there something inside something else? So I'm going to try letting u equal what's inside, not including the square root, just what's inside the square root, e to the x plus 4. Then du dx is equal to the derivative of e to the x plus 4 is just e to the x. And I'm going to rewrite this. I'm going to bring that differential over to this side. So du equals e to the x dx. Now we're going to start cutting out this middle step because it's always what's going to happen. We're just going to say if u equals e to the x plus 4, then du equals the derivative of this side, and we'll tag the dx on right away. So we're going to save ourselves one line of writing by excluding that right there. So now I'm going to do, and again, this all comes with practice. We're going to rewrite this integral so maybe we can see this a little bit better. E to the x, because we need e times dx in order to substitute the du. So let's see if you, and this is a matter of just comes with practice. Isn't this equivalent to 1 over, and I'm trying to get the ex next to the dx, 2 square root e to the x plus 4 times e to the x dx. I can either put that up in the numerator or I can change the numerator to 1 and pull that out to the side, because that's still just e to the x over 1. And why do I do that? Because now I can clearly see my substitution. E to the x dx is going to get replaced with du, and what's inside the square root is going to get replaced with u. So this is equivalent to integrating. And I don't say equals because I don't know. I don't feel comfortable writing that right now. we do definite integrals, maybe it'll become more obvious why I don't like doing it. So I just say, all right, we're going to set up a new integral, and we're going to integrate 1 over 2 square root of u, and then e to the x dx is just du. So really, we're just looking for the antiderivative of 1 over 2 square root of u. Now you might see, because we've done it a gazillion times, that the antiderivative of 1 over 2 square root of u is just the square root of u plus c, right? Why? Because the derivative of u to the 1/2 power is 1/2 u to the negative 1/2, so this is something you just might remember. Or note, if you weren't sure, 1 over 2 square root of u is equal to 1/2 times u to the negative 1/2. We write it as a power function. So the integral of 1/2 u to the negative 1/2 with respect to u. I'm just going to leave the power, the coefficient out front, so that's just that 1/2. And then we're going to add 1 to the power, so negative 1/2 plus 1 is 1/2. And we're going to put the reciprocal power out front. 1 over 2 times 2 over 1 is just u to the 1/2, which is the square root of u. All right, so now that being said, we now have the answer to our problem. So the answer is, we started with e to the x, 2 over the square root of e to the x plus 4 dx is equal to, the square root of u, the square root of what we called u, e to the x plus 4 plus c. Check this by taking the derivative, and you'll see that it works. All right, moving right along. Let's look at this. 3x squared times x cubed plus 5 to the 50th power. Now, if you had all the time in the world, you could actually sit here and multiply x cubed plus 5 times x cubed plus 5 times x cubed plus 5. You could do that 50 times, and you could get a 152nd degree polynomial, perhaps? No, it'd actually be way more than that. No, that should be about right. X cubed to the 50th. Yeah, about 152nd degree polynomial, but that would take a really long time. But what I want you to do is notice that we have something inside the parentheses. What's inside the parentheses is x cubed plus 5. So think to yourself, I see something inside. What's the derivative of what's inside? 3x squared. Cool, that's what's outside. So we're going to let u equal what's inside the parentheses. X cubed plus 5, because it's what's inside, so we can integrate just u to the 50th. So remember, I'm going to skip a step right here. I'm just going to say the derivative of x cubed plus 5 is 3x squared. The derivative of 5 is 0, and we're going to tag on this differential dx. Don't forget that. So now we have 3x squared, x cubed plus 5 to the 50th dx. I'm going to rewrite this, and again, the more comfortable you get with these problems, you won't have to rewrite this. I'm looking for 3x squared dx, so I'm just going to literally rearrange my multiplication and call this 3x squared dx. So now I'm going to replace this with du, and I'll replace what's inside the parentheses with u. So what I'm actually integrating is u to the 50th power du. So integrating 3x squared times x cubed plus 5 to the 50th power with respect to x is equivalent to integrating u to the 50th power with respect to u. Super easy problem, because we just raise the power by 1 and divide by the new power, or if you want to treat it as a product, you can put the reciprocal out front. So u to the 51 divided by 51 is equivalent to 1/51st u to the 51 plus c. All right, so now let's go back and write our answer, because that's it. We have to go back and put it in terms of x. So my answer is the antiderivative, or the integral, of 3x squared times x cubed plus 5 to the 50th power dx is equivalent to 1 over 51. But instead of u, I'm going to replace u with x cubed plus 5 to the 51st power plus c. Again, take the derivative. We bring the power out front. The 51 and the 1 over 51 cancel. Leave what's inside alone. Drop the power by 1. That gives us this piece. And then multiply by the derivative of what's inside. And that's this piece. So substitution is reversing the chain rule. So in order to reverse the chain rule, you have to have something of the form where you have a function inside of a function and its derivative outside. So this only works if that process can be done, if that's set up like that. All right, all is well and good in this problem, but what if we didn't have the 3? Then du would be 3x squared, and we would get stuck with this extra 3 straggling around. But we can compensate for that. So if we don't have the exact derivative, but we have a multiple of the derivative, we can still do this. All right, so this is the same problem, except I eliminated the 3, so almost the same problem. So this is still my inside function. So I'm going to let u equal x cubed plus 5. Whoops. Right? Just plus 5. Then du is equal to 3x squared dx. Now the problem is I can replace this with u, but then I only have x squared dx. But that's not a big deal because I have x squared dx here, and I can easily compensate and get rid of that 3 by bringing it over to the other side. So isn't this equivalent to 1/3 times du equals x squared dx? Right. So if I take my problem, x squared, x cubed plus 5 to the 50th power dx. And again, you'll get into a habit where you won't need to rearrange this, but this is x cubed plus 5 to the 50th power. Then I have x squared dx. Right? I'm going to replace the x cubed plus 5, what's in here, with u. Then x dx isn't just du anymore because we had this 3 that wasn't here. So I had to solve for x squared dx because that's what I'm replacing, and that's going to give me 1/3 du. So now let's get rid of the x's and write this all in terms of u. So this is equivalent to u to the 5th times 1/3 du. But don't forget we have that rule, our rules of integration, where we can put constants out front. This is just equivalent to 1/3 the integral of u to the 5th du. So don't let constants that are constant factors trip us up. I'm just going to bring it out front, and now it's going to go along for the ride. So we can easily integrate u to the 5th. I'm just going to ignore this right now. So the antiderivative of u to the 5th is 1/6 u to the 6th, right, plus c. I'm just going to multiply the constants together. We don't need to multiply this constant by 1/3 because this is an arbitrary constant. So an arbitrary constant times 1/3 is still just an arbitrary constant. So we typically just kind of leave that as a dangle around the end. So this is going to be 1/18 u to the 6th. Oh, goodness, hold on. I changed the problem. Backpedal. U to the 50th. I'm so sorry. I did not mean to do that. So this is going to be u to the 51st power. Oh, yuck. I like the other one better. So we'll make that 1 over 51, u to the 51 power, which is 1 over 100 and, why did I change that? 3 times 51 is 153. U to the 51 plus c. Oh, that's much more awful. But don't make that mistake. Don't copy the problem incorrectly. It's u to the 50th, not u to the 5th. So we change this to u to the 50th times 1/3 du, bring the constant out front, and then we're integrating u to the 50th, which will be 1 over 51 u to the 51. The 1/3 just goes along for the ride. 3 times 51 is 153, u to the 51. Now remember, we have to put it back into terms of x, so therefore my answer, the integral of x squared, x cubed plus 5 to the 50th power with respect to x is 1 over 153. In u, we put u back in, and u was right here, x cubed plus 5, right, to the 51st power plus c. And again, go ahead, take the derivative of that. I guarantee you it will become the integrand once you simplify it. Huh. Sorry. Didn't mean to make that mistake. All right, let's keep going. The integral of the tangent of x. So I believe somewhere along the lines I gave you the answer to this, but I'm going to derive the answer. Note, the tangent of x is equal to the sine of x over the cosine of x. Agree? So, that being said, the integral of the tangent of x dx is equivalent to the sine of x over the cosine of x dx. Now notice we have a function and its derivative here. The derivative of the sine is cosine, and the derivative of the cosine is the negative sine. So we can use substitution to evaluate this integral. I'm going to tell you right now, we have to let u equal the cosine. And I'll show you what would happen afterwards if we let u be the sine. So then the derivative of u is the negative sine of x, d of x, dx. But we only have sine x dx, so I've got to bring this negative over to the other side. So negative du will replace the sine x dx. So we have the tangent of x dx, which is equivalent to the sine of x over the cosine of x dx, which is, I'm just going to pull this apart for simplicity. And again, this just comes with practice. Sine x dx, right? It's 1 over the cosine times the sine x dx. I'm now going to replace sine x dx with negative du. And I'm going to replace the cosine with u. So really what I'm integrating is 1 over u negative du. But we treat this as negative 1. So it's negative 1 over u du. And the antiderivative of 1 over u is the natural log of u. But we have this negative out front. So negative natural log of u plus c. Right now we're going to introduce a technicality which we've sort of ignored up until this point. We're assuming here that everything behaves nicely and that u is positive. But no one said that u had to be positive. So in that case, if we tried to integrate 1 over u and get the natural log of u, and u was not positive, then this would be nonsense. So what I'm going to do, and we'll explain it after, I'm going to throw in the absolute value. So regardless if u is positive or negative, we'll take its absolute value before we take its natural log, and things will work out nicely. All right, so that being said, we now have our answer. The integral of the tangent of x dx is equal to the negative natural log of the absolute value of the cosine of x plus c. So now you have to be careful here because there are different ways to express this. You may have seen, I think this is what we actually did in our notes previously. We called the negative natural log of the cosine the positive natural log of the secant. So either one of these are perfectly acceptable antiderivatives of the tangent of x. So how can this equal this? Well, keep in mind the negative natural log of the cosine of x. Numerical values out front of logs can be rewritten as powers of what's inside the log. So this is the natural log of the cosine of x to the negative 1, which is the natural log of 1 over the absolute value of the cosine of x, which is the natural log of the absolute value of 1 over the cosine of x, because 1 is just positive, so we can absorb it in there. But 1 over the cosine is the secant. Right? So therefore, the antiderivative of the tangent, if you look in tables, sometimes your book is going to use the negative natural log of the absolute value of the cosine plus c, but that's equivalent to the natural log of the absolute value of the secant of c. Either one of these, when you take its derivative, in return will give us the tangent. So again, we're going to revisit this probably in the next lecture. This one's getting a little lengthy, so I might end after a problem or two. And then, let's see, I got a couple more here. Oh, I got a lot more. Maybe I'll do one more, and then I'll end it for you guys to take a break, and then you can finish up in part 2. Actually, I'm going to do 2 of them because these 2 are related. So, okay. Function inside of a function. So here's my inside function. It's pretty obvious because x to the 5th is inside the secant squared. So we're going to let u equal x to the 5th. Then du is just the derivative of x to the 5th, which is 5x to the 4th. And don't forget the differential because du dx equals 5x to the 4th. We just brought the dx over to the right-hand side. So notice there's no 5 here. We're going to replace this with u, and all that's left is x to the 4th and dx. So we have this extra 5 right here. So I'm going to bring the 5 on the right over to the left and call this 1/5 du is x to the 4th dx. So again, you can, at some point, you won't need to rewrite this, and I'll eventually stop rewriting it. Secant x to the 4th, secant squared of x to the 5th dx. And I'm just going to put that x to the 4th next to the dx. So what we see here is the secant squared of x to the 5th dx. Nope, I lost it, sorry. This is also why I have to stop after 30 minutes because I start getting loopy, right? X to the 4th dx. So now I'm going to replace this with 1/5 du, and I'm going to replace this with just u. So what I'm actually integrating is the secant squared of u times 1/5 du. Always bring these dangling constants out front if it's multiplication. So if a constant factor is inside the integrand, we can bring it out. Secant squared of u. So integrating x to the 4th, secant squared of x to the 5th dx is equivalent to integrating 1/5 secant squared u du. All right, a constant out front just goes along for the ride. The antiderivative of the secant squared of u. Now this is just how well, oh my gosh, I'm off the page. I'm sorry. This is how good you remember your derivatives. The antiderivative of the secant squared is the, excellent, tangent of u plus c. So the antiderivative of the secant squared of u times 1/5 du is just 1/5 tangent of u. So now let's just finish this up. So therefore, my final answer, the antiderivative of x to the 4th, secant squared x to the 5th dx is equal to 1/5 tangent. We started with x's, we need to end with x's. It's going to be tangent of x to the 5th plus c. All right, so just one more problem. We'll take a break. All right, look at this. And you might be like, oh, that's just the same thing we did. Well, this one has the extra 2 where the other one didn't. And the derivative of x to the 5th is not 2x to the 4th. So I'm just throwing this one out there because I see students make mistakes with these constants. So don't make this harder than it has to be. We're still going to let u equal x to the 5th, then du equals 5x to the 4th dx, right? But the thing is, I have 2x to the 4th, and here I have 5. So there's several ways you can algebraically compensate for that. I can multiply both sides of this by 2/5. Or it might be easier for you to see this. Let's just first get rid of that coefficient first. So 1/5 du equals x to the 4th dx, but we need a 2 out front. We need 2x to the 4th. So now let's multiply both sides by the 2 to get the needed coefficient on the right-hand side. So if u equals x to the 5th, du is 5x to the 4th dx, and 2/5 du will be the needed 2x to the 4th dx. So you can do some algebraic manipulation here. Here I got rid of the incorrect coefficient completely by bringing it over to this side. Then I was left with a coefficient of 1, which needed to be 2, so then I multiplied by 2. So now when we set this all up, I'm going to rearrange this right now. I have secant squared of x to the 5th times 2x to the 4th dx. All right, so this is going to get replaced with 2/5 du. This is going to be my u. So I'm really integrating secant squared of u times 2/5 du. I'm going to bring that 2/5 out front. So constants are super important. We can't just ignore them. Secant squared of u du. So secant squared u times 2/5 du. We can bring the 2/5 out front. This 2/5 can just go for the ride. The antiderivative of the secant squared is the tangent of u plus our arbitrary constant. So therefore we can finish it up. My answer is 2x to the 4th secant squared of x to the 5th dx. Final answer is 2/5 tangent, and instead of u was x to the 5th plus c. All right, so I'm going to take a break, and I'm going to say, here, I'll write this right here, to be continued, part 2. All right, guys, see you in a few minutes.